So in this section I would like to take the time to break down the effect into smaller pieces, cover a little bit of vector maths, and anticipate potential problems. So first of all, if this is a trajectory of the particle, and this would be the parent particle, then what we want is a splitting operation that sort of gives us this kind of circular pattern of the resultant split particles. So in order to do that, we need to break down several components. First of all, we need to be able to calculate a vector, say for instance this vector over there, this one, that is perpendicular to the vector, or so that the angle between them is 90 degrees, that's perpendicular to the velocity vector of the particle. In order to do that, we need to calculate a few products. We can calculate a cross product and a dot product. The cross product is fairly straightforward. It's going to give us sort of the resultant vector. The dot product can help us define if it is possible to calculate the cross product, and if it is not possible, then we're going to have to use another vector to calculate the cross product. It'll all become clear once we sort of break it down further. So then, say that we've got the resultant vector. What we will be doing then is sort of multiplying this around the velocity axis with a ratio. Yeah? So if there's, say, 20 particles, then we're gonna multiply this with each time 1/20th of a circle. So 1/20th of 360 degrees. And each section will sort of have like a little bit of an angle of that 360 degrees between them. Or we can randomize this, or we can kind of spread it out evenly depending on the number of particles. Okay, so let's see how we can get to the cross product. So, the cross product, if we have two vectors, a vector A and a vector B, and we want to calculate the resultant vector, which kind of is perpendicular to it, then what we can do is we can use the cross product, which will give us the resultant vector C, which is perpendicular to A and to B. Now, vector A and vector B, they kind of form a plane. A plane can be defined by them, and the C vector will be standing 90 degrees angle on top of that plane, so will be perpendicular to that plane. The way it works in Houdini to calculate a cross is there is a cross function, and it takes in two vectors, an A vector and a B vector, and the resultant vector would be C. So, if I break down the formula a bit further, then we can see that the A vector actually consists of three components. We've got the X component, the Y component, and the Z component. I've kind of written it in the Houdini format a little bit with $signs and the vector 3 expression, which kind of defines the format of the kind of vector that we need. Okay, so the vectors that we will be working with in particular will be originally the velocity vector and the translation vector, the position vector of the particles. So, alright, so let's put these vectors into this cross expression. So what we get is this resultant C vector is a cross product of the first vector, vector A, and the second vector, vector B. Now the problem is that as we do this, vector A might be a lot bigger, a lot longer. The length of vector A might be a lot bigger than, say, vector B. Now the resultant vector will still be perpendicular, but the length of A or B, depending, will influence the length of C. We don't necessarily want that. We want to have a clean result. So in order to get that clean result, we can either normalize the inputs, so say normalize A and normalize B, and then put them into the cross product, or we can just simply normalize the resultant vector. So this is what is being done there. So a normalize operation is put around the calculation of the cross vector. What that does is basically makes sure that the length, the total length of the resultant vector is equal to 1 and not a smaller number or a bigger number. Now in some cases the cross product will not be able to be calculated, and we will have to come up with a solution for those scenarios. Okay, one more thing is that the way we will be inputting it into Houdini is by putting in the individual components, so the X component of this cross product resultant vector. And the way to go about doing that is all the way on the end add a little index. So if we have the resultant vector of this normalize operation, and we add this little index operation, 0, 1, and 2, we can access the individual components of that vector. So 0 corresponds with x, y is 1, and z will be 2. Okay. So let's have a look at the potential cross products and the particle's trajectory. If this would be the trajectory of a particle, and we've got these distinct points where we're going to sort of analyze what's going on with the vectors that we will be using to calculate this splitting, these perpendicular velocity vectors, then let's analyze what happens at these distinct points. First of all, let's have a look at the first point. Yeah. What happens in the first point? The velocity is going up, so the particle will go from point 1 to 3, 4, 5. So the velocity is going up, but since we will be using the position of the particle, so sort of the translation factor, at the beginning where the particle is 0, 0, 0, the translation factor will be 0, which will result in an incorrect calculation of the cross product. Now, this is, you can kind of define an initial vector if you wish, but we can in this case sort of ignore this one because we are emitting every 20 frames. So if we say like, okay, we will be emitting at frame 20, frame 40, that's a lot later than frame 1. So this case will just be ignored. Now we will see where other cases sort of are similar and that we will be using sort of a solution to that. Okay. So in point 2 over there, say that the velocity vector is still going straight up, yeah, and now the translation vector or the position vector is also going straight up. The problem is that these vectors are overlapping and they're not defining a plane. We need this plane to be defined in order to get a good result out of our cross product. So again, the solution underneath is use a custom vector instead of t. So what we will be doing later on is just adding, say, a point there, yeah, and we will find out, are these two sort of overlapping or close to overlapping? If they are overlapping or close to overlapping, we will be using a different vector. You will see how that kind of will help to calculate the plane, which will in terms will help to calculate the cross product. Okay, point 3. In point 3, everything is sort of fine, so the velocity vector is going in one way, in one direction. The position vector is going from the origin to position 3, yeah, and their components are different, which basically means that they will define a plane. One more thing, this situation could also mean that say the translation is going upwards and the velocity is going downwards. So this can either mean they lie on top of one another or there is 180 degrees difference in their angle. Okay. In point 4, so in position 4, let's assume that, say, the particle kind of speeds up, yeah, goes through point 3, and then at point 4 it slows down and the velocity sort of becomes really small, sort of 0. Yeah? So, if the velocity becomes 0, that means we don't have a velocity vector anymore to calculate the particle's perpendicular vector anymore. So what we can do is we can use the last known good velocity. So, say that the length of the velocity vector goes down, which basically means the particle is speeding down, it's kind of slowing down. So it's going slower, 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 slower. Well, at some point we kind of want to have a threshold and say, okay, if the particle goes any slower than this, we're just not going to store the new velocity vector anymore, and we're going to use the old velocity vector. The advantage of this is that, say that the particle is slowing down, yeah, and it's stopped, it can still be splitting off new particles, and the new particles will kind of, split as you would expect them to have split from the last good velocity. Yeah? So that's kind of a solution to that. This one actually comes with a small problem, is that if we put the threshold sort of too high, then very slow velocity, sort of that if the particle is not completely stopped, but it's kind of going really slow, yeah, it can change direction, yeah. But then once it starts to speed up, it will pick up that new vector and use that. So it's not such a big problem if we kind of change our threshold. In point 5, again, the particle is sort of, even though it's not aligned with one of the main axes, it's not aligned with y or x or z, but if it goes far enough from the origin, then the velocity vector and the sort of origin, the position vector, will start to overlap as well. When these two will start to overlap, we will get the same situation as in point 2, sort of that the plane is not, not being able to calculate anymore, so we can't calculate our cross vector anymore, our cross product anymore, and so we will have to use a custom vector in that case as well. Again, this scenario can be analyzed using the dot product. So what exactly is the difference between a dot product and a cross product? A cross product, I'm not going to go into the deep maths behind it, you can find that in a maths book or online, but a cross product is important to know that it will return a vector, whereas a dot product will return a scalar. So a scalar value is one value, whereas a vector value will return 3, so A, B and C. So what we can do with a dot product then, in the following example, is we can find out if these vectors are overlapping. So say that from A and B we use a dot product, and this is the way to kind of get that dot product. So in the same way we'll be kind of implementing that into Houdini as we did with the cross product, and we will get a resultant scalar value. So this is not a vector anymore, so this is not A, B, C, but this is one value. This is one floating point value. So as you can see, what happens is that vector B basically is being projected onto vector A. So, and if these the result that is returned is normalized, so basically it will be between 1 and 0. 1 being they are completely overlapping, which means vector A, when vector A is being projected on vector B, it will take up sort of entirely vector B, and it will return 1. However, if we've got like a 90-degree angle between them, then the projection of vector B, as you can see, will sort of give a point, sort of give a 0 distance, and will return a value of 0. And anything in between, any angle in between, as you can see, it kind of grows from an angle of 0 to sort of, this is 45 degrees, this is 75 degrees-ish, and this is 90 degrees. And the dot product will kind of vary between 1 and 0, so as you can see it fades off. Now why is this useful? Well, we can use this to kind of analyze when they are overlapping, and if they are 1 or close to 1, so say anything over 0.95, we will have to use a custom vector. We will have to use another vector. So let's introduce the case of a custom vector. Okay, so let's first look at this. So there's the original trajectory. So what happens when, say, in position 2, so this is the original case, where position 2 overlaps. If I start to introduce a custom vector, so if I test it with my dot product, if I know, okay, my dot product in this case will be equal to 1 or something close to 1, so anything higher, say, than 0.95, we will be using, instead of t, we will be using a custom vector. I've named it u, it doesn't really matter the name, but as long as it is, sort of not lying on one of the main axes, or not lying on the particle, or well, there are still error scenarios where the original position and the particle position is in between the origin, the particle, and the u vector, but this is a lot more rare scenario than when a particle lines up with one of the main axes. So let's introduce the resultant vector. So instead of now using the position vector, we are using the custom vector. So as you can see at the moment, it's using the velocity vector, which is going straight up, and it's using the custom vector, which is sort of on the side over there, and this will generate another plane. That's good, because now we can use this vector to calculate the perpendicular using the cross product to that plane. Okay, so I hope you kind of followed that. We will now start to implement that back into Houdini with several different attributes.